Okay, we're going to talk about sound. Specifically, we're going to talk about the speed of sound um, and echoes. Okay, so let's just do. So see here, put this in. Speed of sound. So as we talked about earlier, um, what sound is it's a traveling of a wave through air, and the mode of passage is from molecule to molecule of air, um, gradually sort of spreading out from the source, you know. And if we have a vibrating source, be this a voice box or a speaker coil or a drum or a guitar or any of that sort of thing, okay, well, that starts a forward and reverse oscillation, which then transfers its way from molecule to molecule right throughout the air. Okay, um, this is a longitudinal wave, right? So it's a back and forth wave. You can imagine it as areas of compression and areas of rarefaction. So where the air is spread out, it's rarefied air, and where the air is compressed, it's a compression zone. Okay, so this is kind of how sound goes. Um, when I ask you, when we talk about the speed of sound, what do you think the speed of sound is based on? What factors might play into how fast a sound wave can travel through air? Okay, maybe the density of air. And what affects the density of air? What sorts of things would affect it? Sure, okay, that might play a role. What else? Maybe pressure, right? If you compress a gas, it gets more dense. Temperature, good. Okay, specifically, these two, although they are probably, important if we really want a very, very, precise and accurate measure of the speed of sound and air, um, are not as, I don't think, important maybe as temperature is. The pressure variation of normal air is not super high from day to day, week to week, month to month. Moisture content sort of rises and falls depending on the time of year. It's not something we really study in this unit. But definitely temperature is more what we're going to look at here. Now, if that has something to do with density, I mean, it may or it may not. Um, but definitely temperature will change something about the molecules in the air. And specifically, what will it change about the molecules in the air? As we raise the temperature, what changes about the molecules in the air? Yeah, exactly. Molecules travel faster, they vibrate faster, they randomly move around. Molecules travel faster when you have a higher temperature. So when the temperature is higher. Yes. And it's all leading towards kind of a little formula that we're going to be using to talk about this. So here's a question. I want you to think about this. Will sound travel faster on a cold day or a warm day? So it turns out we were sort of divided on what we thought, but one argument is that it should be faster when it's cold. Okay, this is argument one. Faster when cold. Why? Because the molecules should be closer together. Okay. And the other argument is it should be faster when it's warm because molecules collide more often. And you need that physical contact between molecules in order for sound waves to travel. So faster and warm because molecules collide more often. And in fact, the second you want postulate is true. Sound does indeed travel faster on warm days. I guess the effect of the higher level of collisions outweighs the closer together scenario. And there's actually a little, it's not really, it's an approximate formula. Okay, so here's an approximate formula. And again, since there's other factors than just temperature affecting the rate at which sound travels, this only sort of is, it's close, but it's probably not exactly right. And it goes like this. 331 plus 0.6 t should equal the speed of sound. Where, and I guess we need units, right? This should be meters per second. Where T is Celsius temperature. Okay. Now, this is an interesting little formula. And just as an aside, I want to show you something about it. You should know this from math class, right? You learned that in math class? Yeah, this is the equation for a line where this is the slope. Oops, not the slope. The slope. This is the slope. This is your sorry. This is your independent variable. Independent variable. And this is your dependent variable. I don't know if you use that terminology in math or not. But if you look at our little formula we've just kind of revealed here, y, so this is the speed of sound, is y. Speed of sound is equal to 0.6 times the Kelvin temperature plus 331. So let's imagine that we make a little graph here. Okay? Let's make a little graph here. I'll slow down in just a second, let you catch up. I just want to make a little graph first. Okay? Now let's imagine that on the x-axis, we've got T, which is degrees Celsius. And on the y-axis, we have the speed of sound. Okay? Where is the, and this is 0 degrees C, and this is like rising temps, and this is falling temps. On a 0 degree day, what is the speed of sound? On a 0 degree day, what is the speed of sound? Right, 331. So this is the y-intercept of this little graph here, right? And what you'd end up with is you'd end up with this kind of scenario going on based on the way that's set up. Okay? Sound increases in speed the warmer you get and decreases the cooler you get, and at 0 degrees Celsius, right? 0.6 times 0 is 0, so 331 is your y-intercept. So here's an application of something that you learn in math class, and here's a real-life example of where it plays a role. Okay, let's try a problem using this, and this might be something that you would see on a quiz. Okay, I guess I want pen mode though, not. You clap your hands, yeah, and you hear an echo. 1.2 seconds later. If it is 20 degrees Celsius out, how far away is the wall creating the echo? Echo. Okay, so let's draw a picture just so we understand this. I like to draw stickmen. It's like very fun. And oh yeah, we could do that. Stickman with a gut. Okay, so we clap, right? And like, let's say over here we have a nice wall. Here it is. There it is. There's our wall. Let's get a brick wall. A brick wall. Okay. So the first thing to notice and remember about a question like this is 1.2 seconds is the time it takes for the sound wave to go to the wall, follow the law of reflection, and come all the way back. So assuming the velocity in the air is constant, how long does it take to just go there? Well, it would take half of this time, right? It would take 1.2 seconds if that's the total time divided by 2, or 0.6 seconds this way, and 0.6 seconds back the other way. That's important. Oftentimes people will forget that, and they'll just use 1.2, and the wall will be twice as far away as it should be. So before we can continue with this, we'll need to sort out how fast the sound is moving. So just learn speed is 331 meters per second plus 0.6 times t. T in our case is 20 degrees. So 0.6 of that should be 12. Okay, so we get 331 meters per second plus 12 equals 343 meters per second. Okay, and then we have to dig into our mind vault and remember when we had d equals velocity times time, right? So the distance to the wall, d here, should be the velocity of sound, 343 meters per second, times 0.6 seconds, because that's how long it takes to get to the wall. And from that we will get, so we get 205.8 meters. And that's good.